All right, welcome. In this explainer, we are going to demystify the statistical tools you see every single day in medical literature. We'll break down how researchers can go from a tiny study to making these huge conclusions, and maybe more importantly, what all those numbers in the research papers really mean for your day-to-day practice.
So here's how we're going to tackle this. We've broken it all down into 5 key parts. We're going to start with the fundamental challenge of pretty much any study, then walk through the formal process researchers use, we'll decode that famous p-value, and finally, we'll get to what really matters for your patients. Okay, let's dive in.
So let's kick things off with the absolute core problem that every single clinical researcher has to face. I mean, this is the very reason inferential statistics even exist in the first place. Think about it. It's not possible to test a new treatment on every patient in the world, right? So the big challenge is this. How can we confidently make that leap from what we observe in our small sample group all the way to the entire patient population?
And that is exactly the job of inferential statistics. It's the whole point. It gives us the mathematical framework to build a reliable bridge from the data we actually have to the much, much larger population we really care about. Okay, so how do researchers actually do this? How do you formally test a claim, like whether a new drug works, using only your sample data? Well, the answer is a really structured process called hypothesis testing.
The best way to think about it is like a scientific court case for our data. It's this formal 4-step process that lets us decide if the patterns we're seeing in our little sample are because of a real effect or if it's all just random chance.
So, the whole process kicks off with 2 competing claims. On one side, you've got the null hypothesis. That's the default skeptical position that our new drug does absolutely nothing. And on the other side, you've got the alternative hypothesis. That's the claim we're actually hoping is true, that there is a real effect.
Now, this is a really important mental shift. We never actually try to prove our ideas right. Instead, the entire system is built around trying to gather enough convincing evidence to reject that no-effect idea, to throw out the null hypothesis. And that leads us directly to one of the most famous and, let's be honest, most misunderstood numbers in all of medical research, the p-value.
Okay, let's break that down because that sounds a little dense, right? The p-value is basically a measure of surprise. It asks this question. If the drug truly did nothing, what are the odds we'd get results like these just by pure random luck? So a low p-value means our results would be really, really surprising if the drug was actually useless.
And this quote just illustrates the idea so well. It's like this. If a new drug had no effect, getting a p-value of 0.05 means you'd only see results this strong about 5% of the time just by chance. Think of it like finding a lung nodule in a young, healthy non-smoker. Is it proof of cancer? No, of course not. But it's surprising enough that it makes you say, whoa, okay, we need to investigate this further. That's what a low p-value does.
And that brings us to the magic number 0.05. For decades, this has been the widely accepted, though frankly pretty arbitrary, line in the sand. If a study's p-value dips below this threshold, the result is officially labeled statistically significant, and the researchers get to reject that null hypothesis.
But, and this is a huge but, a small p-value is not the end of the story. Not even close. Because the result can be statistically significant without being even remotely meaningful to your patients. And that brings us to what really matters.
You know, if you only take one thing away from this whole explainer, please let it be this. Statistical significance and clinical significance are 2 completely different things. One just tells you if an effect is likely real, while the other tells you if it's big enough to actually care about.
Here is the perfect example. So imagine a massive study finds a new drug lowers blood pressure by a single solitary point. With enough people in the trial, that result could be highly statistically significant with a teeny tiny p-value. But is a 1-point drop in blood pressure going to change a patient's life? No, absolutely not. And this is exactly why we need a better toolkit than just the p-value. We need to look at the effect size, which tells us the magnitude of the effect. Is it big or small? And we need the confidence interval, which gives us a plausible range for the true effect. It's kind of like the difference between saying, hey, I hit the target, versus saying, I hit the bullseye, and I'm 95% confident the true center is within this tiny circle. See the difference?
Okay, so you're reading a paper and you see these names like t-test or chi-square. How on earth do researchers pick from the dozens of tests that are out there? Well, it usually boils down to one key distinction.
You can kind of think of these tests in two big families. You've got your parametric tests. Those are like the power tools. They're strong and precise, but they make a big assumption that your data follows a nice, pretty bell curve. Then you have the non-parametric tests. They're more like a flexible multi-tool. They don't make that assumption, which makes them great for messier, real-world data.
So, for instance, if you're comparing the average blood pressure between two groups, you're probably going to see a parametric t-test. But if you're comparing something categorical, like how many people in each group improved versus did not improve, then a non-parametric chi-square test is the right tool for the job.
But this is so important to remember. All of these things, the tests, the p-values, the confidence intervals, they are just tools. They're designed to help us quantify uncertainty and give us evidence, but they can never, ever replace your expert clinical judgment.
So the next time you pick up a journal article, I want you to ask yourself this question. Are you just going to stop at the p-value, or are you going to search for the true patient value? Look for the effect size, examine that confidence interval, and ask yourself, is this result not just statistically real, but is it clinically meaningful? Because that is how we turn good evidence into great patient care.